Thanks a lot, and thanks for the organizers for the opportunity to speak today. So my name is Bulla. I'm a senior research scientist here at Stockholm University, and today I'll try and convince you that polarimetry is a useful tool to study the geometry of compact object mergers. This is the work in collaboration with many different people, including like Stefano and Klaas that should be in the audience. So let's start maybe with this event like GW17 or 17, which I guess most of you might be familiar with. This was a gravitational wave event detected by LIGO in 2017. That was followed only a couple of seconds later by gamma ray detection, which of course trigger a lot of excitement around the globe, and people pointing their telescope towards the location where those two signals were coming from. And finally, about 11 hours later, a new transient was found that in this galaxy that was not present in an archival image taken 21 days before, but popped up as a new transient. And this was actually confirmed later by the entire community to be the electromagnetic counterpart of this gravitational wave event. And of course, I mean, I won't have time to go into everything we learned from this single event. But one thing is this event proved the connection between binary neutron star mergers and short gamma ray bursts. So this signal was consistent with a binary neutron star merger, and the gamma ray detection proved that kind of this gamma ray burst that was seen proved that connection basically. But not just the short gamma ray bursts were seen, but also this so-called kilonova or macronova, which is basically an electromagnetic transient powered by the radioactive decay of our process nuclei. And so basically during these mergers of two neutron star or a neutron star and black hole, you eject some material that is very hot and dense, and you create these very heavy elements via our process that are very unstable. So the radioactive decay and this decay actually powers these so-called kilonova. And the broad agreement within the community was that in terms of light curves and spectra, this event could be interpreted as a combination of two components, so two different ejecta components. So this they could power two different components, so-called blue kilonova and red kilonova. So for this talk, I guess the main the main point here is that the red kilonova is powered by a red component where the conditions are such that you can create very heavy elements, and this means these elements have a lot of transitions, which translate into quite high bound line opacities, and I'll get back to that later. But the agreement was also that there has to be a second component, so-called blue component, where relatively lighter elements were produced with fewer transitions and lower line opacities, and this will be important for the rest of the talk. So there is this general agreement in terms of light curves and spectra, but there are still many open questions, and here are just a few. So first of all, we don't have a direct evidence of these blue components, so the presence and especially the properties of these blue components are still uncertain. Second the second question is about the inclination of the system, that at least at the time this event was discovered was relatively uncertain. So we don't know, we didn't know the viewing angle precisely, and that has an impact on different aspects like calculating the rates of these kilonovae or measuring the Hubble constant. And of course, this question could be answered by polarimetry. So, and here I'm talking about linear polarization, where the polarization will be sensitive to the ejecta geometry, and we do know that these are very far from spherical symmetry. It will be sensitive to the inclination of the system, the distribution of the elements within the ejecta, but also the interplay between the different opacities. And so in these events, the main source of opacities are electron scattering, which is polarizing. This is Thomson scattering, which is polarizing and wavelength independent, at least in this optical range. But we do have these bound light transitions from these R process elements that is thought to depolarize the radiation and have a strong wavelength dependence. And so polarization, polarimetry could help answering those questions. And actually for this specific event, polarimetry was taken. This is a work led by Stefano in 2017, where multiple epochs of VLT imaging polarimetry were taken. And here, these are shown in the QU plane. So these are the 4 epochs. You might say, okay, we do see some polarization at the level roughly of 0.5% or so. But then if you overplot like the field stars, you see that they all end up in the same region. And so the conclusion from that paper was that the polarization we were seeing was mostly due to the interstellar medium in our own galaxy. But the question is, how can we estimate the intrinsic polarization since there is this wide range in the field stars? And so perhaps another question was how much polarized it really was this event and how much polarized are kilonovae. And these were the question we had in mind when we started this project a few years ago. And so we decided to use this code that I was developing at that time. And this is a Monte Carlo ready to transfer code to model flux and polarization spectra in supernovae and kilonovae. And we did use like sophisticated state-of-the-art opacities for these R process elements that you can see here, where the different colors are the different components that I mentioned before. And you can see that the electron scattering, which is these 2 dashed lines, are pretty similar between the 2 components. But what is really different is these bound line opacities that I mentioned before, where in one case, in the red component, the line opacity is dominating, at least in this optical range, while in the blue component, you get like wavelengths, red wavelengths in the optical, near infrared, where the electron scattering is dominant, or at least comparable to line transition. And so the idea we had in mind is that we might expect some polarization from this blue component. And so this is the sketch we had in mind. So you had these 2 components, as I mentioned, and if a photon travels and gets scattered here in the blue component, it is likely that scattering is electron scattering. So the photon that reaches the observer is polarized, while all the photons interacting in this red component would be unpolarized. And this will kind of break the spherical symmetry that you might have and give you some polarization. And so we did test these hypotheses and run some simulations, and these are the findings. So first of all, here I'm showing the polarization as a function of viewing angle, going from an equatorial viewing angle, where the projection of the model will look like this, to the polar viewing angle, where you would get a circular symmetry, basically. And you can see that in this case, you will get 0 polarization here, but then that polarization level increases to roughly 0.8%. And so this means that if we do detect a polarization in a future kilonova, that will prove that this blue component really exists and could help estimating constraining some of the properties. But one other surprising thing was that the polarization very rapidly drops to 0. So you can see here, by the way, this is a 7,000 angstrom, but you can see that already at 3 days or so after the merger, the polarization is 0, which means that we need to be fast to detect this signal in the future. But this is also quite interesting because then this modeling tells you that you shouldn't see any intrinsic polarization at these late phases. And so one could use these late phases, observations to estimate the interstellar contribution, and then use it to subtract it from the previous epochs where you might get some intrinsic signal. And this is what we did. So we could, for this specific event, constrain the polarization to less than roughly 0.2% for GW17 or S17 kilonova. And at the same time, this also put some constraints on the viewing angle based on the comparison between models and data. And so we could basically constrain the inclination to 60 degrees or so from the polar orientation, which is not that constraining, but in the future we might get better constraints if we do detect a polarization level. And then my final slide would be about this more recent paper we did on the modeling of Kilonova polarization in black hole neutron star systems, where actually the question about the presence of a blue component is still an open question. So it's still unclear from the modeling of these systems whether we should see a blue component. And here you can see the polarization spectra in this case for different viewing angles in 2 different cases. One where we do not have this blue component, but just a red component, and one where you also have a blue component. And you can kind of convince yourselves that the spectra are quite different, that one could actually constrain the presence of these blue components. So in one case, you would only get near infrared polarization levels, quite high for some viewing angle. In the other case, you would get also some optical polarization. So this is, I think, getting more kilonova in the future, and hopefully relatively nearby that we can get polarimetry would be really useful to answer some of these questions. So I'm not sure, probably I'm running out of time, so I'll stop here, but I'm happy to take any question here or on Slack. Thanks.